Hi, I'm Hanglu. I'm from the Advertisement, and I'm going to be talking about formal languages and left-orderable groups. The work that I'm going to be talking about is done with Equivalence and Cristobalitas, and it's going to be about my second paper. So first, what's a left-orderable group? A group is left-orderable if there exists a total order on the group such that that order is invariant in their left multiplication. So G smaller than H if and only if F times G is smaller than F times H for all elements G, H, and F in G. So why study left-orderable groups? Let me give you 4 applications. First, there's a large class of groups which are left-orderable. For example, all surface groups except the one for the projective plane are left-orderable. Rags and virtually poly groups are left-orderable. Second, we have a link with dynamics. So for a countable group G, G is left-orderable if and only if it's isomorphic to a subgroup of the set of orientation-preserving homeomorphisms on R. So if you didn't like the definition for left-orderable groups, maybe you can just think of our left-orderable groups as these subgroups. Third, left-orderable groups were used by Minier in a proof of the Hahnemann-Neumann conjecture. So the conjecture says that if H and K are non-trivial free groups, then the rank of H intersecting K minus 1 is less or equal to the rank of H minus 1 times the rank of K minus 1. And finally, left-orderable groups are related to the zero divisor conjecture, which is famous in the group ring area of study. So let R be a ring without zero divisors, and let G be torsion free. Then the conjecture says that the group ring RG has no zero divisors. And what is known is that if G is left-orderable, then RG has no zero divisors. So let's look at a first example of a left-orderable group. I've left the definition on top so you can follow along. So the integers, with respect to addition, has a natural left order given by, well, what you think is natural left order. So minus 1 is smaller than 0, smaller than 1 is smaller than 2, etc. The order is clearly invariant under addition, right? And since the definition of a left order is completely symmetric, then we also have that 1 is smaller than 0, is smaller than minus 1, etc. is another left order. So now let's define an equivalent notion, which are positive cones. So we can look at left orders in terms of sets called positive cones. And that way we don't have to keep up with, every element being bigger than another, and we can just look at a set. So roughly speaking, a positive cone is trying to capture the notion of additive positivity in your group. So P is a subset of G, and it's a positive cone if P is closed in a subgroup operation. So you can imagine if you add two positive things, you get another positive thing. And also G is partition between positives, inverse of positive, and the identity element, which we call the trichotomy property. So for example, Z with respect to addition emits a positive cone, which are all the positive elements. Now we said that positive cones are an equivalent notion to left-orderable groups, so Z also emits another positive cone, because Z has 2 orders, right? Which is just all the negative elements. Z mod NZ, or any group with torsion, does not emit a positive cone, because suppose that you have a group with torsion, and suppose that that has a positive cone, then there's some elements G, which, such that G to the n is equal to 1. And without loss of generality, G is in P, but that would mean that G to the n is equal to 1, and that's in P by the semigroup closure property. That's a contradiction because 1 cannot be in the positive cone by the trichotomy property. So for example, we had the integers, which emitted this natural left order. And now a left order is equivalent to defining positive elements. So take P to be all the integers which are greater than 0. And we mean that in the sense that x is smaller than y if and only if minus x plus y is greater than 1, right? Now in general, if you have a left order, then you can define a positive cone P by defining that as all the elements G and G which are greater than the identity. Moreover, defining a positive cone also defines an order. So you can define that G is smaller than H if and only if G inverse H is in P. Think of this as left multiplying both sides by G inverse. You would get that 1 is smaller than G inverse H. And that's what you want it to mean by saying that G inverse H is in P. We're not going to prove the general statement, but you can do it as an exercise, and it's really quite straightforward. So let's look at our first closure property. So left orders are closed through subgroups. So if G is a left-orderable group and H is a subgroup of G, then H inherits the left order from G. Clearly, if G is smaller than H, if and only if F times G is smaller than F times H for all G, H, F, and G, then this is also true for all G, H, and F in H. For example, the subgroup of even integers inherits the natural order on the integers. So for the second closure property, closure under extensions, let's start with an example. So we know that Z is left-orderable. Now Z squared is also left-orderable viewed as equal Z. Here I've drawn a kilograph for Z squared, and I've drawn a positive clone for Z squared given by the green dots. So a positive clone for Z squared is given by a to the b to the n, where n is positive or n is equal to 0 and n is greater than 0. We call this a lexicographic order leading factor A, where A is the circuit generated by the A generator. And we say that because we decide if an element is positive by first projecting into the A coordinate, checking if the A coordinate is positive, and if not, if it's neutral, then we project to the B coordinate and we check if the B coordinate is positive. So note that a positive clone is given by the PA, BB, and PB, right? That's what we said, where PA and PB are positive clones for Z. So this idea of composing positive clones generalizes to extensions. Suppose that you have this short exact sequence 1 goes to n goes to g goes to q goes to 1, where n is the kernel and stands for normal subgroup, and q is the image and stands for quotient, such that n has positive clone Pn and q has positive clone Pq. Then we claim that PQn union Pn is a positive clone for G, since every element can be written as G is equal to Qn, where Q is in Q and N is in N. So how do we show that? So first, well, if you have this decomposition, then G is such that its Q factor is either in PQ or in PQ inverse, or Q is equal to 1, right, by the trichotomy property of PQ. And then you have the same thing for N. So, okay, G is really partitioned into PQN union Pn, disjoint union with PQN union Pn inverse, disjoint union with 1. For the second closure property, if G and H are in P such that G is equal to Qn and H is equal to Pn, then you want to say that GH is in P. And the way you're going to do that is that you're going to rewrite GH in the appropriate form. So GH is equal to Qn Pn, but we want to slide the P on the left, right? So we conjugate N with P, and so we get that that's equal to QP, P inverse NP, N. And now your N is in a normal subgroup, N, so it's going to be some other element of N once it's conjugated. So you get that GH is equal to QP N prime N, where N prime is in N. So now you have your GH in regard for, and then you can check that it's in the positive clone. So either Q or P are in PQ, in which case GH is in PQN, which is in P. Or Q and P are both equal to 1, right? In which case N prime is equal to P inverse NP, but P is equal to 1, so that's just equal to N. And then we know that if both Q and P is equal to 1, then both N and N have to be in Pn. So GH is in Pn, which is also in P. So we call this lexicographic order, or lexicographic order of the leading factor Q. So this is the end of the basics. Now let's get to talking about research. So let's talk about finite generation. So recall that we had a positive cone for z squared that was given by two finitely generated positive cones, P and PB. So just positive cones given by all the positive A's and the positive cone given by all the positive B's, such that PAB union PB is a positive cone for z squared. So in some sense, it's as easy to know if something is positive in z squared as it was for z, but this positive cone for z squared is not finitely generated.
In fact, z squared also inherits an isomorphic positive cone as a subgroup of index 2 in the Klein-Bottle group with generators AB and relation A inverse B AB. And the Klein-Bottle group will have positive cone generated by A and B. So here I wrote this notation AB plus, which means that you get the semigroup generated by A's and B's. And what that means is that you get the set of all positive words over A and B. And by positive word, I mean that there are no A inverses or B inverses in the words, only A's and B's. And now z squared will be generated by A squared B. So below, I've drawn a Cayley graph for the Klein-Bottle group. And in green, I've drawn the positive elements in this Klein-Bottle group. And the semigroup A and B, well, that's a positive cone because as you can see, it covers about half the graph minus the identity. And this is allowed because the orientation on the B-axis is alternating. So if this Cayley graph was a z squared, then if you took only positive elements in the A and B axis, then you would see that it would only cover the upper right half of the Cayley graph, right? But because we're the Klein-Bottle group, A and B are enough to cover about half of the Klein-Bottle group. In darker green, I've highlighted the elements which are both positive and in z squared, and you can see that in this Klein-Bottle group, the positive elements of z squared are isomorphic to the positive elements that you had before for z as an extension of z cross c viewed lexicographically. And again, this inherited positive cone, which was inherited from a finitely generated positive cone, is not finitely generated. So you might be wondering, well, maybe you picked a bad positive cone for z squared, and z squared has another positive cone which is finitely generated. But it's just the fact that z squared has no finitely generated positive cones. We won't have time to show this in this talk, but this is, roughly speaking, given by the topological fact that the space of left orders of z squared, denoted L of z squared, has no isolated points. And if you were to have a finitely generated positive cones, that would imply an isolated point in the space of left orders. So being finitely generated is not closed into picking extensions, as we saw with z squared as z cross z, and it's not closed into picking finite index subgroups, as we saw with z squared being a subgroup of index 2 in the Klein-Bottle group. So the takeaway is that being finitely generated is not a very good property to describe how hard it is to determine whether something is in a positive cone. Our research motivation is to have a good way to describe positive cone complexity, and we will study positive cones in regular languages, or more generally, positive cones and formal languages, which is a superclass to which regular languages belong to.
So first of all, what's a positive cone language? So suppose that G is finitely generated, and let X star be the set of all the words over X. A language is a subset L over all the words in X, and the elements of L are called words. Makes sense, right? So a language is just a collection of words over some alphabet. Now we say that L evaluates to P if there's an evaluation map from x star, so all the words of x, to g, such that pi of L is equal to p. So so you have words over the generators of g, which map to g. So for example, x inverse maps to 1. And we just want a collection of words which map to p. Now, if p is a positive clone, we call L a positive clone language. Furthermore, if p has a language L, which evaluates to it and L is regular, then L is called a regular positive clone language, and p is called a regular positive clone. So what's a regular language? So a regular language is a language accepted by a finite set automaton. And finite set automata capture the idea of needing finite meaning. For example, this automaton accepts the language of binary strings with an odd number of zeros. So here you start at the start state, which is the state on the left, which has the arrow from the word leading to it. And you say, okay, well, I'm remembering that I have an even number of zeros. So if I start inputting a 1 as a first letter of my word, then I still have an even number of zeros. But for example, if my second letter is a 0, then now I have an odd number of zeros. So I go to this state with double circle, which is an accept state. Now, if your word was only 1 0, then at this point you would accept it, and so you say that 1 0 is part of your language. However, if you have more letters to a word, then you continue inputting. So if you input more ones, then you stay at the state with the 0. So that's why you have an arrow from 1 pointing to the state itself. But now if you have another 0, then you go back to remembering that you had an even number of zeros. And now you can input more ones, but that's not going to change that. And so that's what a finite set automaton is. So basically it's just all the words that you read, which go from the start state to the final state, with the help of the labeled arrows, and all the words which lead to the final state are the accepted language. So examples of accepted strings would be 1 0, as you said, 0 0 0, and 0 1. And you can check that just by following the arrows. Non-examples would be the empty word 1 0 0. And regular languages are the simplest languages in a classification of languages called the Chomsky hierarchy. So here, I just wanted to show you that a positive clone for Z squared can be represented as a regular language. So here we have a P and PB, and we have a P of Z squared with PAB and PB, where PA is just positive A's and PB is just positive B's, right? And you can see here an automaton that accepts only positive A's, an automaton that accepts only positive B's, an automaton for P, which is just all the numbers of the P inverse, and then PB, PAB, and PB is just a combination of these automaton on the top. So an automaton represented PAB and PB is basically given by when you start at the start state and you either go into the automaton representing PA, followed by the automaton representing B, or you start at the start state and you go to the automaton representing PB. So an important point to highlight is that when L represents P, we only need that for every positive element in P, there exists at least one word of L such that the evaluation of that word is equal to G. For example, we know automaton for Z, PA. PA admits a positive language given by A to the N, where N is positive. So A squared A inverse is not in this regular language for PA, even though it represents a positive element. This is very different from the word problem, which is about the pre-image language of the identity, so all the words mapping to the identity. Yet positive languages are related to the word problem, since if W is in a positive language, then clearly it doesn't equate to 1, because it got something in P, which is the string P, and therefore W is not really the word problem. So here's a limit. If G is such that the preimage language of one of its positive rings is regular, then G is trivial. So this justifies why we have such a definition for our languages evaluating to P, why we only require that one word represents each element that's positive, because if we had the whole preimage language being regular, then G is trivial, so we really want to study that. So now let's overview our research niche. So let's first look at closure properties of regular positive clones and some results. So first of all, regular positive clones are placed into extensions. The proof is really easy and basically what we saw with the positive clone squared. Second, regular positive clones are also placed into finite index subgroups as we wanted. This is a proof in my first paper. And well, the proof is not as easy, but doable. Third, having a regular positive clone is independent of generating sets, assuming that the generating sets are finite. This is a known fact and also easy proof. And finally, and I put a little star around it because if we have time, we will prove it. Regularity is positive clone dependent. So depending on the positive clone, it may be more or less easy to figure out if something's in it. So for example, B1Q, where Q is greater than 1, so the bomb-squad accelerator group, 1 and Q as parameters, has both regular and non-regular positive clones. And this is a result in an upcoming paper that I'm telling you. So now let's look at some geometric properties of regular positive clones. So definition, a set P and G is coarsely connected if it's connected in a Cayley graph up to some R neighborhood, to some R greater or equal to 0. So here's a result. If you have a regular positive clone P, then the set P is coarsely connected. This is a result of Alonso and London Cristobal Rivas. And as an application, non-abelian free groups have no coarsely connected positive clones. And hyperbolic groups, which you can think of as slightly thickened abelian free groups, if you want, have some coarsely connected positive clones, but they have to be very distorted in the sense of not being connected by quasi-geodesics. Again, that's a result of Alonso and Cristobal Rivas. Relatedly, free products, so a generalization of non-abelian free groups, have no regular positive clones. This is a result of Bergman Schmidt. So, slightly weaker result on a larger set. And asymmetrically hyperbolic groups, which are generalization of hyperbolic groups, have no regular quasi-geodesic positive clones. So we don't know if they have any coarsely connected positive clones, but if they were, they would also have to be very distorted. And this is a result in my first paper.
As a final research topic I would like to introduce, I want to talk about crossing left-orderable groups with Z. Something inherent about positive cones change when you cross groups with Z. For example, let A and B be left-orderable. Then A free product with B has no isolated orders. This can be found in a textbook written by Duran, Navas, Cristobal Rivas. And in particular, F2 has no isolated orders. However, the free group of two elements cross Z has both isolated and non-isolated orders. This is a result of Duran and Cristobal Rivas. And moreover, F2 cross Z has a finitely generated positive clone. So remember that finitely generated implies isolated. This finitely generated positive clone is part of a new family of groups with K finitely generated positive clones for any K greater or equal to 3. This was a result in my first paper. And this is interesting because whether such a family existed was a question left open by Navas in 2011. In general, free products of groups with regular positive clones, denote them A star B, have a one-counted order. This is a result of Dixon-Schmidt. but no regular order by a result of elimination. And we're going to prove this. So A star B plus Z, though, will have a regular order. And this is a result in our upcoming paper.
So, okay, let's get into the proofs now. And we'll start with the geometric interpretation of regularity. So remember, P is regular if P is closely connected. And I chose this as the first proof because we'll use it in a subsequent proof, and this one is a little more straightforward with the other ones. So let's get to it. So if L is a regular language such that the evaluation of L is P, we will show that there exists some R such that for every word in L there exists an R path, P, which is a concatenation of P1 to Pn, such that P is from 1 to the evaluation of W, such that the PIs are from P to P, except for P1, which starts at 1, and such that the length of the PIs are small or equal to 1. This is why it's called an R path. So let's see that in action. So, okay, take your word W, which is x1 up to xn, and your prefix WI, which is the prefix, so it goes from x1 up to xn. Now for every prefix W, there exists an associated word UI, such that WI UI is in L. And UI is smaller or equal to the number of states of L in terms of length. So the proof of that is very easy. So imagine your WI coming from the start state of your automaton and going up to some other state. So now you've hit a certain number of states, right? You're at some state. And now, well, how many more states do you have to go through to go to your accept state? Well, less than the number of states in your automaton, right? So now just take U to be the shortest word, leading you from the state at which WI stopped into the accept state. Then UI is going to be in length less or equal to the number of states, clearly. Okay, so now you can take the path, let's say evaluation of UI minus 1 inverse, xi UI, to be a path of length smaller than 2 number of states plus 1. And that path is going to be from P to P, right? Except for P1, which is from 1 to P. And such that the evaluation of P1 to Pn leads to the evaluation of W. So just to clarify this, so you took your word WI, and now UI puts it in P, in the positive cone. So then UI inverse goes from the positive cone to the endpoint of WI, and then you follow that by an xi plus 1, and then you put this WI plus 1 into P again. So the path UI inverse xi plus 1 UI is a path from positive cone to positive cone with the right properties, and then if you check the length of that path, it's going to be smaller than 2 regularity of s plus 1 because each UI is smaller than the number of states in length, and xi has no 1. And yeah, that's your little PI, or PI plus 1. Anyway, now you set R to be just 2 times the number of states plus 1, and now P is R connected. Now let's talk about the result of regularity being positive cone dependent. So the theorem was that E1Q with generators AB and relation ABA inverse is equal to BQ, where Q is greater or equal to 1, has both regular and non-regular positive cones. So let's start by looking at what a non-regular positive cone looks like. So note that there's a well-known isomorphism between B1Q and the semi-direct product of the Q-adic rationals with the integers, where in this isomorphism, A acts by conjugation on B, such that K over Q to the n, so an element in these Q-adic rationals, corresponds to A to the minus n, B to the K, A to the n. Okay, you can check that this does match the relation, since AB A inverse is equal to 1 over Q to the minus 1, then AQ is equal to Q. Now, every element G in B1Q can be just written in normal form when you start with the quotient, so that's some A to the n, and then you put in an element of the rational, so that's A to the minus n, B to the n. Therefore, we have a lexicographic order given by a positive function C times Z to the Q-adic rationals union a positive form for the Q-adic rationals, as we saw by our extension model. Alright, so what does this lexicographic order give us? Why does it give us that this positive cone is not regular? So here in this figure, we've drawn the kilograph of B12, but this generalizes to B1Q. So because of this lexicographic order, a positive cone is given by picking everything above the zero level of the tree, or everything below the zero level, because the levels of the tree, or the blue arrows, give us our Z. Now, because of the tree structure, this set is not coarsely connected, because if you look at branches of the same level, in order to connect them, you'd have to go down some levels. But for every R, there exist two branches above zero, which are connected by going way down, more than R levels. And remember that not being closely connected implies not regular, so this positive cone is not regular. So what about a regular positive cone for B1Q? So B1Q has an embedding rho into the set of orientation preserving homomorphisms on R, given by rho of A of x is equal to qx, and rho of B of x is equal to x plus 1 for x and R. And we can check that this map preserves the relation as expected. Now, if you write G in normal form, so G is equal to A to the n, A to the minus n, B to the k, A to the n, then rho of G of x will be equal to Q to the n of x plus K over Q to the n. Then you can check that this implies that rho is injected as a So now let P naught be equal to the set of elements such that its dynamic polarizations and 0 is something greater than 0. Then this defines positivity in G except for the stabilizer of 0, since any element in this set acts by a fixation of relation. Now, the stabilizer of 0 is just A, right? Because A sends x to Qn of x, so it's in 0 to 0. So P can be given by P naught union a positive cone for the separate group generated property. This gives us that P is equal to A to the n where n is greater than 0, union A to the n, A to the minus n, B to the k, and A to the n where k is positive. And that has a regular language representation. This next figure is just to show that there's an automaton which accepts a language representing P. So now let's talk about free products of groups with regular positive cones. Those have a one-counted positive cone. So definition, a one-counter language is a language which is accepted by a finite set of automaton with a stack. So for example, we have a one-counter automaton accepting the language 0 to the n, 1 to the n, where n is greater than 0. And this language would not be accepted by a finite set automaton because one would have to remember the n exponent, which can be arbitrarily large, and that exceeds what a finite amount of memory can be included in. So the automaton we illustrated below, what it does is that it reads zeros, and for each 0 that it reads, it pushes the symbol into the stack, and then for each 1 that it reads, it pops the symbol from the stack. So I've written that in sort of formal notation, but you don't really have to understand the notation to understand what I said. So once a stack is empty, then you accept the word. It's clear that the set of one-counter languages contains a set of regular languages because one-counter automata are just regular automata with extra properties. So now let's show that free products of groups with regular positive terms have a one-counter positive term. So for every free product, we label the factors as GIs, where the i's are indexed from 1 to n. And now we write each element as its free product normal form. So write G as G1 to Gn, where each of those factors are in a single group factor, and such that two consecutive factors for the element G doesn't belong to the same group factor, and such that each factor for the element G is not equal to 1. And now, from this normal form, we define a function going from G to the integers, where tau of G is equal to the number of positive syllables of G minus the number of negative syllables of G plus the numbers of risers of G minus the number of false of G. So a positive syllable here is when the GI is in the positive column of its correct factor, and then the negative syllable is when it's in the negative column, and rise is when two consecutive element factor are such that the index of the group factor of the first one is smaller than the index of the group factor of the second one, and a fall is when the index of the group factor of the first element factor is smaller than the index of the second element. So now, let's look at some properties of tau, which we won't prove previously. So tau of G is equal to 0 if and only G is equal to 1. And this is due to the normal form that you write G in to calculate this tau. Moreover, tau is odd when G minus the identity, since the number of syllables plus the number of risers or falls is odd. This is just because for every 2 syllables, you have 1 rise, right, in between every 2 syllables. So it's like, if you think about the number of syllables as vertices and the number of rises as edges in between the syllables, then the total number of vertices plus edge is odd. And finally, tau of GH minus tau G plus tau of H would be an absolute value smaller or equal to 1. And you can check that by just doing a page check. So now this function tau defines a positive cone with the elements of G whose tau output are greater than 0. And that's because for all G and G, tau G is either greater than 0 or smaller than 0, and this G is equal to 1. So that implies that G is partitioned properly. Moreover, if G and H are in this positive form that we define, then tau of GH is equal to tau of G plus tau of H plus from epsilon, where epsilon is minus 1, 0, or 1. But since both tau of G and tau of H are greater or equal to 1, right, because tau is 3 integers, we get that tau gh is greater or equal to 2 plus epsilon, which is greater or equal to 1. So that gives us the subgroup closure property. So the one counter complexity is given by counting tau. Then in our paper, we give this as a transducer. So here's a transducer which reads input words in F2 in the normal form, in the free product normal form. And then some edges you see have an extra label given by this \t or \t inverse. And that just means that at this edge, you're going to read the input symbol, and then the \t means that if it's t, then you push into the step, and if it's t inverse, you pop off the step. So there is a good equivalence between that and being a one counter. And this is just to illustrate that F2 is one counter. So now let's talk about the theorem that free products of groups with regular positive cones, class C, have a regular and thus closely connected positive cone. So this means that there's a nice group theoretical interpretation to one counter. And the intuition is that we transfer the tau counter into the Z factor. So for an element GZ in G plus Z, we would like tau of G plus Z to be greater than 0 to define. The problem is that if we define a function as such, the kernel of tau would be too large. So we wouldn't be just the identity which would be in the kernel. So the fix that we use is that we use a tau odd function, and we let the positive cone of G plus Z be defined as the element GZ such that tau prime, which is equal to tau of G plus 2Z, is greater than 0. So at the automaton level, what happens? So we don't have a stack anymore to play with, right? So we want to replace the \t or t inverse labels by something. So what we do is that we replace labels of the form x/t squared. So you read x and you push in two symbols onto the stack by x z inverse to sort of compensate for the positivity, so that instead of counting tau as you did when you had a stack, you always try to maintain the tau, or tau prime in this case, count to 0, so that you don't have to count anything. And then before accepting the word, we force at least z to be appended at the end. So your tau prime count is always 0, and at the end you append at least one z so that your tau prime count is greater than 0. And then you can append as many z's as you want, because the more positive, the better your argument positive cone. But the point is that you want everything that you accept to be in a positive cone, right? So that's why you append at least one z. However, the problem is that we can't replace things of the form x over t. So when you input one symbol in the stack by things like xz to the -1/2, right? It doesn't make sense. It's just a letter. So we need to multiply each previous state that we had in the one counter automaton with +1 -1 and 0, which will memorize the offset value of your tau prime from 0. So basically, like, your tau prime count knows it's not going to be quite 0, but it's going to be near by +1 -1. And you'll use the finite amount of memory to memorize that offset. Okay, so this is an example of a regular positive cone for F2 plus Z. So don't be scared by the seeming complexity of it. As you see, if you compare that to the one counter automaton for F2, this is really just a one counter automaton with every state tripled and like a couple of extra states and extra arrows to go in between those. And the automaton functions as we described, and this is just to show you that this automaton is indeed regular, and you'll just have to trust me that it accepts a positive code for efficacy. All right, so this is the end of my talk. Give yourself a big clap for getting through all these proofs. You really did it. And yeah, I hope you enjoyed it and learned something. All right, now let me do a bit of advertisement. So if somehow you didn't get enough of this and you're interested to know, for example, why L of z squared, so the space of leftovers of z squared, has no finitely generated positive cones, I display the results in my first paper. So that regular positive cones are basically finite unit subgroups that asymmetrically hyperbolic groups do not have quasi-tridic positive cones. That F2 cross Z has a finitely generated positive cone, and the existence of a new infinite family of groups which have k-generated positive cone for any k greater than 3. You can go on my website, homeomorphism.com. There's a good quality recording available about my first paper with also